Dear Chairman, thank you very much for your kind introduction. And thank you very much for inviting me. I'm Matthias Arnold, Technical Lead of the Let's OPC UA Joint Work Group. During the next 45 minutes, I will introduce you to Let's OPC UA, the upcoming common language for laboratory and analytical devices. What is the current situation in the laboratory and analytical domain with regards to digitalization, especially connectivity? In a typical lab, you will find a mixed assortment of highly specialized devices, provided by very different equipment manufacturers. Some of the vendors highly specialized, some of them with a very broad portfolio. These devices produce data, such as analytical results in a variety of data formats, ranging from text-based formats like CSV to XLS, PDFs, and very often vendor-specific closed formats. However, when it comes to standardizing data formats, there are few glimmers on the horizon. Allotrop, ADF, or Animal, to name two prominent examples. But what about device connectivity in the lab and analytical domain? The current situation is somewhat reminiscent of the dark ages in automation before the introduction of OPC. Different communication interfaces, if any at all. A lot of them still with serial interfaces talking vendor-specific protocols with very limited documentation. Modern devices might have USB connectors or even some Ethernet capabilities. However, when it comes to open, standardized protocols, you're 90% lost in no man's land. The current situation is hindering digitalization in the laboratory and analytical domain, or, as Joachim Richard, Vice President, Analytical Sciences, BASF, vividly puts it, no standards, no digital transformation of the lab. True integration requires more standardization in the fields of communication and data exchange. So, we urgently need standards. That's the reason why we founded Let's as companion specification on the proven and established industrial integration standard OPC UA. Standards are the foundation for driving digital transformation in the laboratory and analytical domain, improving data integrity, costs to the results, reproducibility of experiments and processes, increased automation and thus increased efficiency, and last but not least, fair data, machine-based learnings and machine-based insights, to name just a few. What are we trying to achieve? We aim for true plug-and-play integration of lab and analytical devices along the laboratory workflow. Seamless connectivity of devices with an absolute minimum of configuration necessary, if any at all. We are all aware that such connectivity is hard to achieve in our domain. It is hard to establish plug-and-play interoperability between the many different lab and analytical devices on one side, and all the different applications like SCADA, LIMS, ELN, data asset or service management on the other side. We, the team behind the Let's OPC UA joint work group, are trying to overcome at least some of the obstacles with an OPC UA based communication protocol that addresses some of the most important common use cases in the laboratory domain. What are the use cases we are targeting? First, remote monitoring, alarms, notifications. This is the foundation, because if you cannot see what is going on, you cannot decide or act. Monitoring is complemented by remote control, so you can start or stop functions, change parameters or set points and so on. The remote monitoring and control use cases are the foundation for automation. Second, program management and orchestration. For example, listing all the programs on the instrument, selecting a program to be executed, starting the program run, monitoring the program's progress, and so on. For most devices, especially analyzers, result data is generated. This data usually resides on the instrument before being uploaded to an application like a data system. The program management and result management use cases form the basis for orchestrating instruments along workflows. Third, the use cases required for asset management, such as condition monitoring, maintenance service, calibration, validation, and so on, they are the foundation for business cases such as enhanced serviceability. Put in a nutshell, LETS supports the use cases automation, orchestration, service, and asset management. When we started the LETS initiative, we did not want to reinvent the wheel. We wanted to build our work on a proven and secure foundation. So why did we choose OPCUA? Because OPCUA is secure. This is a must-have. OPCUA is proven. It is the de facto standard for process industry, pharma, and many others. OPCUA is platform independent, from embedded microcontrollers all the way to cloud-based infrastructure. OPCUA's unique information modeling capabilities is where it really shines. Information modeling is key for plug-and-play interoperability. OPCUA is a true and open standard. OPCUA's cloud support grows fast. This is an evolving requirement for the laboratory and analytical domain. And last but not least, OPCUA offers many reusable building blocks ranging from asset management all the way to referencing semantic definitions in external taxonomies and ontologies. This all sounds like a great foundation for our work. But how can LETS fulfill its promise of interoperable connectivity? We are facing several challenges. Heterogeneity. There are several dimensions of heterogeneity in terms of device types, device vendors, device functionality, complexity, mode of operation, applications, and so on. And future-proofing. How to specify a protocol which is suitable for future device types and their functionality. LETS introduces two concepts to master those challenges. First, the device type agnostic modeling principle. Generic modeling enables plug-and-play interoperability and helps to fulfill the promise of horizontal broad integration. I will introduce you to device type agnostic modeling soon. With its device type agnostic modeling principle, which provides generic patterns and rules, we can master the challenge of integrating different types of instruments. But how can we tell that instrument A is a bioreactor, instrument B is a centrifuge, and for example instrument C is an HPLC? This brings us to the second main principle of LETS. The solution to this question is to provide additional metadata and so-called semantic augmentation. The second principle complements horizontal broad integration capabilities with vertical deep understanding of devices and their information. Among other things, such semantic augmentation enables efficiency gains through machine-based understanding. I will give you an example later in this presentation. In the next slides, I will give you a brief introduction to some of LETS high-level information modeling patterns. First, the hardware view, required for all the use cases around asset management, including serviceability. The hardware view models devices and their components. Devices and components typically have properties like nameplates, date of installation, condition monitoring, status of calibration, validation, and so on. Second, the functional view, which deals with data relevant for the operation, automation, and orchestration of an instrument. A functional unit aggregates functions to achieve a specific outcome and is typically utilized by only one user at a time. Within the functional units, you can find smaller functions which actually do the job, like sensor measurements, closed-loop controllers, and so on. Many laboratory and analytical devices allow the user to define and run programs, also called methods. The program manager organizes such program templates, runs programs, and finally manages the result data generated during the run. In other words, the program manager provides device-level orchestration. How to apply these high-level building blocks to real-world devices? In this example, I will model a centrifuge in LEDs. Let's start with the things we can touch: the device itself and its hardware components. The centrifuge device has a nameplate with standardized layout including manufacturer, device model, serial number, hardware and software revision, and so on. Maintenance-related information, such as condition monitoring properties, is also arranged in a standardized layout. Hardware components, such as lid, rotor, drive, compressor, are modeled in a subtree called component set, with each component exposing its individual nameplate and maintenance-related information in exactly the same way as the device itself. Last but not least, recurrent tasks that affect either the entire device or individual components, such as inspection, maintenance, calibration, validation, cleaning, and so on, can be organized in so-called task sets. Let's continue with the functional aspects of controlling and operating the centrifuge. The functional unit, the yellow box, provides the functional view of the instrument. A device could expose more than one functional unit at a time. For example, consider a parallel bioreactor system, where each individual bioreactor is modeled as a single functional unit, but all of them belong to the same device. However, in the case of our centrifuge example, we deal with only one functional unit. Specific functions are organized in the function set, the green box. In our example, agitation controller, lid controller, temperature controller, and so on. LEDs provides a set of predefined patterns for common functions such as sensors, closed-loop controllers, lids and doors, or whatever. Device-level orchestration is represented by the program manager, the magenta boxes, and works exactly the same whether the device is a centrifuge or an HPLC or a bioprocess controller or whatever. Within the scope of a functional unit, the program manager organizes aspects like program templates, program execution, and results in a standardized way. How do we master heterogeneity with our device type agnostic modeling principle. To demonstrate this, let's compare the Let's OPC UA model of the centrifuge I just presented to you with the model of a completely different device, an HPLC. Although the devices are different, they look very similar from a Let's connectivity point of view. They are both devices with their nameplate. Their hardware components are modeled in the subtree called components set. The functional unit, the yellow box, provides the functional view of the instruments. The instrument-specific functions can be found in the function set, the green box, where all functions adhere to standardized Let's patterns. And last but not least, the program manager, the magenta box, allows device orchestration and is identical for both device types. Bottom line. Over the network, the instruments look pretty much the same. Let's enables plug-and-play interoperability for lab and analytical devices through the device type agnostic modeling principle. To demonstrate the power of Let's information modeling, I will use a workflow orchestration example. This example was created by Helmut Köster's teams at PantaBio during our last hackathon. It utilizes multiple Let's OPC UA enabled devices provided by our Let's proof of concept software. In the first step, PantaBio's workflow application discovers the Let's OPC UA enabled devices and reads their capabilities. Based on this information, a workflow can be planned. Once the workflow is planned, it can be executed by the workflow application. In a final step, the results of the run can be downloaded from the Let's OPC UA devices to the application software. Let's see this nice workflow application in action. This example of workflow orchestration impressively shows that information integration and automation in the laboratory and analytical domain will take a big step forward once standards like Let's OPC UA are established. A big thank you to Helmut Köster and the Panther Bio team for creating this great demonstration. Having introduced you to the first main principle of Let's, which enables broad horizontal integration of different types of devices, we now move to the second main principle, which enables vertical deep understanding of devices and their information. Metadata and semantic augmentation. Let's start with metadata as provided by standard OPC-UA patterns, using the example of a simple process value. At first glance, you learn the name, the current value of the process value. When you take a closer look at the value, you understand that OPC-UA not only provides the value itself, but also information about its current status, such as the signal quality and its exact timestamps. Going deeper, you learn about its data type, access rights, and whether you can query the history of the value from the device. Well, that's not bad. However, more metadata is available. For example, the expected position of the value. The value is used for range as well as its absolute range and, for example, its engineering unit, adhering to a United Nations standard. Bottom line, when looking at a single process value, OPC-UA provides by default a lot of metadata. Now that I have briefly outlined what OPC-UA provides out of the box, let's take a closer look at the wealth of information once we associate semantic definitions with our device data. So, how does semantic augmentation of information work in Let's OPC-UA enabled devices? Ontologies and taxonomies play an important role. For specific application domains, for example process automation or pharmaceutical engineering, ontologies and taxonomies have been developed by standardization bodies and initiatives. The IAC Common Data Dictionaries or ontologies by the Allotrope Foundation are two prominent examples in our domain. In the IAC Common Data Dictionaries for process automation, definitions for items like sensors, sensor technologies, units, closed-loop controllers, or whatever are uniquely defined and organized in hierarchical patterns. The Allotrope ontologies go even further, leveraging semantic web technology for an ontology suite that provides a standard vocabulary and semantic model representing analytical processes in the lab. And here's the trick. By referencing information model items within the Let's OPC-UA information model of the instrument to their corresponding semantic definitions in such ontologies and taxonomies, a strong semantic augmentation of the information model items can be achieved. Such semantic labeling of information is key for a wide range of digital transformation applications and use cases, including, but not limited to, automated configuration, fair data, data-driven reasoning, machine learning and machine insights, and so on. In the following example, I will demonstrate how to associate Let's OPC-UA information model items of an integrated HPLC system with corresponding semantic definitions in the allotrope foundation ontology. As a first step, let us look up some matching definitions in the allotrope ontology. Under the topic equipment, we find a liquid chromatograph system. Looks good. Definitions for reservoirs, pumps, injectors, chromatography column, detectors, and much more are there as well. Even better. Okay, now that we have found semantic definitions for the hardware which makes up our HPLC system, what about items from the functional process and results domain? The column chromatography process, there's a definition, that's very good. Definitions for sample ID, chromatograms, and many more, all there. So far so good. Obviously, we can describe different aspects of the HPLC system utilizing the definitions in the allotrope ontologies. But how can we link this semantic definitions to our data in the Let's OPCU information model of the instrument? Here comes the solution. The HPLC's different components and items that we just discussed have their corresponding representation in the Let's OPCUA information model of the device. OPCUA provides a technology called dictionary references, which helps linking any OPCUA item to an external semantic definition. By leveraging this technology, information in a Let's OPCUA enabled device can easily be augmented with semantic definitions. Bottom line, the resulting high quality and labeled data is the perfect input for applications like data-driven reasoning and insights. Sounds very promising, doesn't it? Here comes an imaginary example to illustrate what can be achieved once well-structured and semantically rich information is available in digital format. An important task in our domain is to match and validate the requirements derived from the process specification, in our example in QC process with two steps called sample preparation and analytics, with the capabilities and performance of instruments. To my knowledge, this task is mainly done manually today, which requires a lot of time, resources, evaluation and paperwork. Whenever the process is changed or different types of instruments must be used for whatever reason, some if not many steps of the validation process must be done again, including extensive updates to the documentation. How could this time-consuming process be supported and partially automated in a digital transformed laboratory with semantically enabled workflow design tools and Let's enabled instruments? First, let's assume that the instruments in the laboratory support Let's and represent their information augmented with semantic definitions from selected well-known taxonomies and ontologies. Second, let's assume that the process definition and all its properties are augmented with semantic definitions from the same well-known taxonomies and ontologies. This means we have machine interpretable descriptions of instruments, including their capabilities and their performance. We have machine interpretable definitions for the process and its requirements. Based on that, let's build a tool for automated validation support. In a first step, the automatic validator learns about the process and its requirements by reading the process definition, including its semantic definitions. In a second step, The process validator scans through the network of Let's OPC UA enabled devices. He identifies potential matches and learns about their individual capabilities and performance. In the third step, the process validator tries to automatically match the process-specific requirements with the capabilities and performance of the instruments. Here, the references to its semantic definitions are of great help. They enable a precise, machine interpretable understanding of the meaning and role of the various information elements found in instruments and the process specification. In the image shown on the slide, the validator just takes a closer look at the detector of the HPLC. The detector type of the instrument, an absorbance detector, meets the specification. Its measurement range meets the specification. The same applies to its precision, and so on. The technologies presented in this example could make applications like the automated validator a reality. This should serve as an example of how the thoughtful combination of information technologies will hopefully enable efficiency gains and quality improvements in complex and tedious tasks such as validation. The key is a machine understandable, standardized representation of the information found in the various systems involved, in this case the workflow tool and the instrument themselves. Let's OPC UA will bring this feature to the world of device connectivity. Now that I have introduced you to Let's OPC UA and its two main principles that enable horizontal broad and vertical deep integration of laboratory and analytical devices, let us turn our attention to the question: where are we today with Let's and what are our deliverables? Let's look at the Let's roadmap. After defining the use cases and the high-level concepts, we started the implementation of the Let's proof of concept. Within the proof of concept, we create a growing number of simulated devices, exposing their data in information models in accordance with Let's patterns and building rules. This allows us to test and optimize the concepts, as well as identify gaps and missing pieces. This proof of concept turned out to be a very useful tool, and we continue improving it. Meanwhile, we authored the first draft of the Let's companion specification. One of the next steps will be reference implementations for clients and servers. We expect to release the Let's companion specification mid to end 2023. Following an agile approach of build, measure, learn, we test and verify our concepts during Let's hackathons, which take place approximately every 6 months. During our last hackathon, participants proved that the dream of plug-and-play interoperability of lab analytical devices into software applications with Let's OPC UA finally comes true. For example, a provider of a workflow planning, visualization and documentation tool was able to plug-and-play integrate different Let's-enabled devices into his application by implementing only one generic driver, all during the hackathon. How is Let's OPC UA organized? Let's is set up as an OPC joint work group. Founding members include a group of device vendors, the OPC Foundation, Medium A, and Spectaris. Spectaris, the German-based Association for Analytical and Lab Technology Vendors, formed the initial nucleus of LEDs. VDMA is instrumental in cross-harmonizing many OPC-UA-based companion specifications for several industries. In addition to the steadily growing number of device vendors and software solution providers, other associations joined LEDs such as Gambica, LabMass, FHI, and of course JIMA. Our user review committee, the LEDs URC, provides valuable feedback with regards to requirements, prioritization, applications, use cases, all the way up to integration testing. Members of our hackathon group Let's Hack implement LEDs into their real-world devices and applications, plus share information on tool chains, technologies and best practices. This setup is complemented by regular exchanges with peer foundations in our domain, like Allotrop Foundation and Bioforum. Finally, the ongoing harmonization with other OPC workgroups avoids redundancy, fosters synergies, compatibility and reuse. If you want to participate in LEDs, join us, be the next. At the end of this presentation, I would like to introduce you to the upcoming KIZ OPC UA companion specification and depict how LEDs and KIZ will nicely play together. The acronym KIZ stands for Common Analytical Instrument System Integration. Its target image is the integration of analytical systems into supervisory data systems, such as chromatography data systems. The KIZ workgroup was founded by Agilent, Shimadzu, Thermo Fisher and Waters. Together they represent a very relevant market share for analytical systems in the fields of liquid chromatography, mass spectroscopy and gas chromatography. The KIZ workgroup was announced during OPC Day 2022 and kicked off in May 2022. The targets of the KIZ workgroup are laid out in their charter. Be standards-based in itself and an independent and active standard for interoperability of analytical instrument with chromatography data systems. Be plug-and-play, be cloud compatible, and it should allow for multi-vendor analytical instrument system composition. It should give analytical instruments more autonomy and flexibility, and it should simplify discovery, enable remote management, support and analytic capabilities. So, how do LEDs and KIZ play together? Complex analytical instrument systems usually consist of several physical devices or modules, such as pumps, column-over detector, mass spectrometer, and so on. See the green box. At the next level up, such analytical instruments are integrated with data systems. The aggregation of physical devices into analytical instrument systems and their integration with data systems is covered by KIZ. The physical analytical devices themselves, including the modules of such an instrument system, are perfectly represented by LEDs. See the blue boxes. In a nutshell, LEDs and KIZ complement each other. Through their close collaboration, LEDs and KIZ are laying the foundation for digitalization of the lab and analytical domain by providing seamlessly integrated OPC-UA-based communication standards for instruments along the workflow, as well as complex analytical systems, including the integration with supervisory data systems. Thank you all for your attention and your interest, and let's OPC UA, the laboratory and analytical device standard. On the slide you will find some links pointing to additional information. Looking forward for your questions and a great discussion. Thank you very much.